Imagine a universe that's not static, not shrinking, but constantly growing bigger. This is the reality we live in. Space itself is expanding, pushing galaxies farther apart like dots on an inflating balloon. But what's driving this cosmic expansion? The answer, it seems, lies in a mysterious force known as dark energy. We can't see dark energy, and we don't fully understand it yet. But we know it's out there, permeating the universe and influencing its evolution. It's like an invisible hand pushing everything outward, counteracting the inward pull of gravity. Understanding dark energy is one of the biggest challenges in modern cosmology. It's a cosmic mystery that has captivated scientists for decades, and it holds the key to unlocking the ultimate fate of our universe. To understand dark energy, we need to go back to the basics of gravity. Albert Einstein, in his groundbreaking theory of general relativity, revolutionized our understanding of this fundamental force. Einstein showed that gravity isn't just a force between objects, it's a curvature in the fabric of space-time itself. Massive objects like stars and planets warp space-time around them, causing other objects to move along these curved paths. Einstein initially believed that the universe was static and unchanging. However, his equations of general relativity predicted an expanding or contracting universe. To counteract this, Einstein introduced a term called the cosmological constant, denoted by the Greek letter lambda. The cosmological constant was a fudge factor that Einstein added to his equations to keep the universe static. He envisioned it as a repulsive force that counterbalanced the attractive force of gravity, preventing the universe from collapsing in on itself. However, just a few years later, astronomer Edwin Hubble made a groundbreaking discovery. The universe wasn't static at all, it was expanding. Hubble observed that distant galaxies were moving away from us, and the farther away they were, the faster they were receding. This observation, known as Hubble's law, provided the first observational evidence for an expanding universe. Einstein, upon learning of Hubble's discovery, famously called the cosmological constant his biggest blunder. For decades, the cosmological constant was largely ignored. However, in the late 1990s, two independent teams of astronomers made a startling discovery that would bring the cosmological constant back into the spotlight. They were studying a special type of exploding star called a Type Ia supernova, which are incredibly bright and can be seen from billions of light-years away. These supernovae serve as standard candles in astronomy because they have a known intrinsic brightness. By measuring the apparent brightness of these distant supernovae, astronomers can determine their distances. What they found was astonishing. The expansion of the universe wasn't constant, it was accelerating. These distant supernovae were dimmer than expected, suggesting that they were farther away than they should be if the universe was expanding at a constant rate. Section 5. The Cosmic Recipe: Unveiling the Dark Sector. The discovery of the accelerating universe sent shockwaves through the scientific community. It meant that there was something else out there, something mysterious and unknown, driving this cosmic acceleration. This mysterious force was dubbed dark energy because it doesn't interact with light or any other form of electromagnetic radiation, making it invisible to our telescopes. Together, dark energy and dark matter, another mysterious component of the universe, make up the so-called dark sector. While dark matter interacts gravitationally, holding galaxies and galaxy clusters together, dark energy acts as a repulsive force, pushing everything apart. According to the latest measurements, dark energy makes up about 68% of the total energy density of the universe. Dark matter accounts for another 27%, leaving only about 5% for ordinary matter, the stuff we're made of and everything we can see. Section 6. Echoes from the Big Bang, the CMB and dark energy. Another piece of evidence for dark energy comes from the cosmic microwave background, or CMB, a faint afterglow of the Big Bang. The CMB is a snapshot of the universe as it was just 380,000 years after the Big Bang, long before stars and galaxies formed. Tiny fluctuations in the temperature and polarization of the CMB provide a wealth of information about the early universe. By studying these fluctuations, cosmologists can determine the composition and geometry of the universe. The CMB data strongly supports the existence of dark energy and its role in the accelerating expansion of the universe. Section 7. Quintessence, a dynamic force shaping the universe. While the cosmological constant is the simplest explanation for dark energy, it's not the only one. Some physicists have proposed alternative theories, one of the most intriguing being quintessence. Quintessence is a hypothetical form of dark energy that's not constant but can vary over time and space. Unlike the cosmological constant, which is thought to be uniform throughout the universe, quintessence could have different properties in different regions of space. This could lead to observable effects that could help us distinguish between the two. However, so far, there's no conclusive evidence to support the existence of quintessence. Section 8. The ongoing quest, unraveling the mysteries of dark energy. The nature of dark energy remains one of the biggest mysteries in modern science. Scientists are working tirelessly to understand what it is, where it comes from, and how it will shape the future of our universe. Some believe that dark energy is an intrinsic property of space itself, while others think it might be a new type of fundamental particle or field. The search for answers continues with groundbreaking telescopes and experiments pushing the boundaries of our knowledge. Understanding dark energy is not just about unraveling a cosmic mystery, it's about understanding the universe we live in and our place within it.